Alright, so let's look at the exciting world of geometric sequences. As always, if you just want to see worked out practice problems, timestamp is in the description below. And just a note, if you're a calculus student looking for geometric series and sequences, I have a video on that. It's not this video. Okay? So this is a natural follow-up to my video on arithmetic sequences. Geometric sequence is typically the second sequence type that you would learn in an Algebra 2 class. Now, if you're not already comfortable with an arithmetic sequence, I highly suggest you go to my video on that because that's typically the first sequence type you learn. Because of that, in my arithmetic sequence video, I talk about what a sequence is, what certain notation means. Here, I'm assuming you're already comfortable with all of that, right? I'm just going to go straight forward into the explanation. So a geometric sequence, like all sequences, it follows a rule, but it follows a specific rule. It's similar to an arithmetic sequence with a key difference. So in a geometric sequence, the next term is obtained by multiplying the previous term by a common ratio. You might find this similar to an arithmetic sequence where instead of multiplying, it's addition, right? That's the key difference between the two. So here's some examples of a geometric sequence. Let's say I got maybe 1, 2, 4, 8, 16, 32, right? And that continues on for forever, really. So why is this a geometric sequence? This is a geometric sequence because in order to get the next number, I'm multiplying by the same number every time, the common ratio. In this case, I'm multiplying by 2. I wrote it 3, but I meant 2, right? Every time I'm multiplying by 2. Now, let's look at another example of a geometric sequence. Let me think. Let's say I'm doing, okay, let's start at 27. And let's say instead of increasing numbers, I'm decreasing numbers. So I go to 27, then I go to 9, then I go to 3, then I go to 1, then I go to 1 over 3, 1 over 9, and that continues on forever. So what's actually happening? What do I have to multiply to 27 to get 9? Well, just some algebra, you could set that up, actually, right? 27 times x equals 9. You'd find out x would have to be 1 over 3. Right, so I multiply by 1/3. 9 to 3, again, I multiply by 1/3. And you'll find that this is consistent throughout. So these are examples of geometric sequences. Now let's go over the explicit and recursive formulas, right? Because we want to be able to describe a sequence, and we can't do that by writing out all the numbers. That would take way too long, all of time. So we're going to need to be able to actually write the formula for the rule. Like mentioned in my arithmetic sequence video, we have an explicit formula and a recursive formula. So explicit formula is here, recursive formula right here. So the explicit formula, I think, is the simpler case, right? It's just a single formula. You just need to know what each part means. So the explicit formula is as follows. A sub n is equal to a1, the first term, multiplied by r, the common ratio, raised to the n minus 1 power, where n is the term we're looking for. So if we're looking for the fifth term, we're looking for a sub 5. It'd be the first term multiplied by the common ratio raised to the 5 minus 1. All right? The recursive case, like mentioned in my previous video, is something that refers to the previous entry, right? So what it says is, okay, a of n is equal to a of n minus 1, the term before a of n. So if you're looking for a of 5, this would be a of 4. Okay, Again, I go over like what these subscripts actually are in my arithmetic sequence video. So it's a of n equals a of n minus 1 times r. Now, when you have a recursive formula, you need like a base case, a starting point. So typically I'll be a of 1 is equal to some number. They would actually give you the first term. Okay? So, the last thing, other than like finding specific terms, some questions might ask you to sum all the terms, right? Like sum the first 10 terms, sum the first 20 terms. Sure, you could add them all up, or you could use a formula. I go over summation notation in my previous video, so I'm not going to go over that here. Not too important, but I will go over the kind of formula for finding the sum of specifically a geometric sequence. Okay, so it's S of n is equal to a of 1, the first term, multiplied by, in the denominator, it's 1 minus the common ratio over 1 minus r to the nth power, right? Where n is like the number of terms you're summing up. So if you're looking for the sum of the first 20 terms, n would be 20. Okay? And that's pretty much covering all you need to know. Like for both arithmetic and geometric sequences, you need to know three things, just three things, all right? Explicit formula, recursive formula, summation formula. Once you got that down, we can go straight into the questions. So let's do that. All right, so one thing you're going to notice if you saw my previous video with arithmetic sequences is that these questions and the arithmetic sequence questions are very, very similar. The reason for that is the type of questions that they're going to ask you, that you could be asked, for sequences in general, are always the same kind of questions. We're just now being asked about a different type of sequence. And that just requires a different set of formulas. Okay, so the first thing we have here is we want to write the ruler formula for the nth term in the following geometric sequence. We're given the first 4 terms. Then we want to find the sum of the first 20 terms in the sequence. Okay, so 1, 3, 9, 27. Let's try to figure out. We need two things, right? We need A1 and we need R, the ratio. So A1, easy, that's the first term. It's 1 in this case. The ratio is simply, let's see what's being multiplied to each thing to get the next term. The way we go from 1 to 3 is by multiplying by 3. And is it consistent the whole time? It seems to be, right? 3 times 3 is 9, times 3 is 27. So the common ratio is 3. Now I'm going to write the explicit and recursive form. So the explicit form, based off what we have here, right, is going to be an equals 1, which you really don't need to write because we're just dealing with multiplication, times 3 raised to the n minus 1 power. And that's pretty much it for the explicit form. Sometimes you might see the n minus 1 in parentheses, just to let people know, hey, the whole thing's in the exponent. And like I said, you don't need this 1 there, so this would just be your final answer. In the explicit form, that was the explicit form. In the recursive form, just to, be familiar with that form as well. A1, you need a base case of 1. A sub n should be equal to a sub n minus 1, right? That's all subscript, multiplied by r. And that's pretty much it. Okay, so that's using these two formulas right here. Now let's find the sum of the first 20 terms. All right, we're looking for sum 20. So that's going to be equal to a1, which is 1, multiplied by 1 minus the ratio, which is 3, to the n power, in this case it's 20, this is going to be a large number, divided by 1 minus the ratio, which is 3. Okay? And that's something we can just put into the a calculator, because there's no way anybody has 3 to the 20th power memorized. And just putting that in, we get, okay, that's a huge number. It looks like 1,773,392,220, which, okay. One thing about geometric sequences is they increase super quickly, right? Just take 1, for example, right? And this is kind of not super important, but 1 multiplied by 2. And let's keep multiplying by 2 just for a little bit. After only about 10, we're already in the thousands. After about 20, we start getting into the millions. And this is the sum of the first 20 of a larger sequence. And I'm not going to bore you with going into the whole thing about, exponential, how fast exponentials change. But that's pretty much it, right? Important things to remember are these two things. Being able to do an arithmetic, a geometric sequence and write it out explicitly and recursively. All right, let's look at the next problem. All right, so here we got somewhat of the same question, similar situation at the very least. We are given the first few terms of a geometric sequence, and it looks like it is an alternating sequence, and I'll go through that in just a second. I'm not going to do this thing because I just realized how large that number is going to be, but we are going to find the 52nd term in the sequence. In order to get the 52nd term, we need to first find the formula. So notice how this number, the next number in the sequence, it's consistently changing signs. That's an alternating sequence. It's alternating between positive and negative numbers. Why does that happen, right? What does this tell us? It actually does give us some information. The same way in increasing geometric sequence means, the number, the ratio, is greater than 1, and a decreasing sequence, right, like I gave an example of here, has a fractional ratio. An alternating geometric sequence has a negative ratio, right? So let's first figure out what our A1 is. That's easy, -1. What is our ratio? -1 times, it looks like -2 would get me +2. Times -2 gets me -4. Times -2 gets me +8. Fantastic. So -2 is my ratio. So let's take the explicit formula. A sub n is equal to -1 multiplied by r to the n minus 1 power. So if we're looking for the 52nd term, it's going to be a sub 52 is equal to the -1st times r raised to the 52nd minus 1 power, which r is obviously -2. Okay, and again, that's just something you would place in your calculator. So you just do -1 multiplied by -2, and you want to be very careful at this point. Your calculator does order of operations, right? It sees something like this, -2, let's say the third, right? Very differently than the way it sees this. Okay, because here, what it's going to do in this case is it's going to do the exponent first, which will be 8, and the answer for this will be -8, right? Whereas the exponent for this, it'll be, actually, I kind of picked a bad example. If I do 4, it'll be -16, right? Which is actually not the same thing as this, because this will be +16. Okay, so be very careful when you put into the calculator, because this is kind of what you want, right? That parenthesis sign there, indicating that, okay, I'm dealing with, I want -2 to the something power, not 2 to the something power, and then multiplied by a -1 at the end. Okay, so very careful. That's a large number. I did not think this through. Let's say instead of the 52nd term, we simply wanted the 8th term. So we'll do a of 8 is equal to -1 times -2 to the 8 minus 1. That's going to be a lot easier. And that gets us 128. All right, hopefully that made sense. Just to kind of go over this problem. What you want to do when it's like, hey, here's a sequence, find the nth term, is first get the explicit formula. From the explicit formula, you can go a bunch of different places. Then just substitute that nth term for n in your formula to find it. That's pretty much it. The other thing I just want to stress is how careful you have to be with this. The amount of times I've seen people just make mistakes and screw up answers completely just because of they're not aware that a calculator reads these two things differently, even though we would not. All right. So now, let's take a look at the next problem. All right. So here we are given the following sequence, and we're also asked to find the formula for the explicit form. Okay. This is the recursive form. Now, for the explicit form, like I was mentioning before, we only need to find a of 1 and the ratio. So a of 1 is already given to us as the base case. Easy enough. So a of 1 is equal to 375. What is r? Well, from the recursive formula, we know r is the thing being multiplied to the a of n minus 1. Oh, this is written out incorrectly. This should be a of n and then a of n minus 1 there. So this thing should be our actual ratio, 1/5. And given that we have a fractional ratio in between 0 and 1, we know this thing's going to be decreasing. Okay, so first let's write the explicit form. It's going to be a of n equal to a1, which is 375, multiplied by r, which is 1/5, raised to the n minus 1 power. Okay, now we want to write out the first 7 terms. So the first term is obviously the one given to us. It's 375. So 375. The next term would be 375 times 5, which is 75. And we just continue this pattern. 15 and then 3. It's 1, 2, 3, 4, 5. Divided by 5. 6 and 7. Okay, so this gets smaller and smaller as you continue. Okay, hopefully these are starting to get pretty easy. I think it's very kind of basic, at least with the exception of what the next problem is going to be. All of the other ones just involve some version of get the explicit formula and do something with it. And with the first one, it was just straight up get the explicit formula. Okay, so now let's look at the last problem. So here we're given the following information. We're given two terms in an geometric sequence. A lot of typos on this one. Two terms in a geometric sequence. And what we want to do is, based off that, write the explicit form of the sequence, the explicit formula. So I'll do this one at a time. First, I'll look at part A. What do we need to write the explicit formula? As always, we need a sub 1 and we need r. Okay, now this is the one thing that's going to differ pretty drastically from the way we did it with arithmetic sequences. Before, I made like the kind of comparison to a linear equation. Because of the way these things are increasing, it's not at a constant rate. You see it's getting smaller and smaller, faster over time, or bigger and bigger, faster over time. We can't use the same trick. We need to figure out a new way. So here's how we do it. First, we're going to kind of write out the explicit formula for each one, right? Because we're looking for r. The first thing we're going to try to find is the rate. So here we have the a sub 4 equals 36. A sub 10 equals 9 over 16. So here's what's going to happen. We're going to almost divide the two with each other in this very specific way. So we're going to have 9 over 16 divided by 36. Okay, and that equals, let's see, 1 over 64. So we got this 1 over 64 by doing the following. We took a sub 10 and a sub 4 and divided them with each other. So let's convert these to what their explicit formulas would look like, right? A sub 10 would be a sub 1 times the common ratio to the 10 minus 1, or to the 9th power, while a sub 4 would be a sub 1 times the common ratio to the 4 minus 1 first power, 4 minus to the power of 4 minus 1, which is 3. Okay? Now we can start simplifying this, and you find that this cancels out, and the r's just simplify to r to the 6th. So this 1 over 64 just equals r to the 6th. And that's something you can take the root of. You take the 6th root of both sides, you end up with a pretty clean answer of 1/2, I believe. I'm just going to double check that. Yeah, 1/2. And that's our common ratio. So all I did was I took the real components, I divided them with each other. Then I kind of took the actual terms, converted it to its explicit formula, and divided them too, in order to isolate r algebraically. Okay, now that I have r, finding the actual term for the first term should be pretty easy, right? So I have a of 1 equal to a of 1. Actually, that's not how we are going to do it. Because we know r, we can figure out a of 1. So I'm going to take this first one. Pick the one that's easiest to work with. Typically, the smaller one will be that. So a sub 4 multiplied by 1/2 raised to the 4 minus 1 power, or 3rd power, should be how we're trying to find a sub 1. Because we know a sub 4 is actually 36. And this is something we can divide, right? So 1 over 2 to the third power should be 1 over 8. And then we have 36 equaling 1 over 8 multiplied by a of 1. And if I multiply by the reciprocal to both sides, I end up with 36 multiplied by 8. And that gets us an a of 1 of 288. All right, so the work here is kind of messy, but hopefully you were able to follow it. The two main steps into getting these pieces of information: first, to get the ratio, take the two terms, divide them, and also divide them in the explicit form, because that is what allows you to isolate the common ratio. Once doing that, pick the term that's easiest to work with. Typically it's going to be the smaller one, and set up the explicit form in that way to isolate a sub 1, because now you know the common ratio. It's just a single variable you're unaware of. That gets you a sub 1. Now that you have that, up here in the top corner, I'll just go on and write that explicit formula. A of n is equal to a sub 1, which is 288, multiplied by r raised to the n minus 1 power. And r is, of course, 1/2, so that's my bad. That's going to be equal to 288 multiplied by 1 over 2 raised to the n minus 1 power. Okay, so there's actually one thing I want to go over that could potentially make this a lot easier. I'm going to derive a much more simplified formula for that. So if you just want to skip ahead a minute, you could do that to just have me do the next, skip to this part B. However, really understanding this, just watching through the next bit, will make you better. Will make you understand this better, get questions right more often, that kind of deal. So in terms of getting the common ratio, let's say I have a term a sub n and a sub m, where m is the smaller one, let's say, and n is the larger one. If I were to write and these are terms in the same sequence, okay? If I were to write this out, the formula explicitly, this would be a sub 1 times r to the n minus 1. This would be a sub 1 times r to the m minus 1. Now, what I did before to find the actual ratio is I divided them. So let's do that here. I did the larger one in the numerator and the smaller one in the denominator. Okay. Then I set that equal to a sub 1 times r to the n minus 1 over a sub 1 times r to the m minus 1. And that's something you could do with equality, right? Now let's start simplifying this stuff. This cancels out, right? You should be familiar with that. This is essentially r to the n minus 1 minus m minus 1. Opening up those parentheses gets me r to the n minus 1 plus m plus 1. Or sorry, this should be minus m, my bad. And then these cancel out. What am I left with? A sub n over a sub m is equal to r to the n minus m. And that is a much easier formula to kind of understand and use than this thing. Okay, so what we're going to do for the next problem is use this formula to get the actual common ratio. Okay? So let's start there on part B. So we have a sub 12 equals 128, and a sub 24 equals 524,288. So we want to write the explicit form. We want to find a sub 1. We want to find the common ratio. Right? Nothing new there. And how do we do that? Well, let's now use this new formula we derived. Okay, so it's going to be a sub n, and the larger one is what I'll make that one. So the larger one, which is 524,288 over 128. Okay, so just punching that in to simplify it, 524,288 divided by 128. That gets us 4096. So 4096 is equal to r raised to the n minus m. R raised to the n minus m, the larger one minus the smaller one, which is just 12. 24 minus 12 is just 12. Now, from here, this is easy. I just take the 12th root of both sides. Something, at this point, you should be just straight up allowed to be using a graphing calculator in this course. So you could just do the 12th root of 4096, getting you that r is equal to 2. Okay? What do you do next? Well, let's pick one of these, the one that's easiest to work with. And like I said, typically it's the smaller one. And let's set up the explicit formula. So a sub 12, which is 128, should be equal to a sub 1 times r, which is 2, raised to the n minus 1, 12 minus 1, which is 11. And that's something we can easily just figure out. So 2 raised to the 11th power is simply 2048. So a sub 1 times 2048, and that's equal to 128. And then I divide by 2048 to both sides. Okay, these obviously cancel. And then 128 divided by 2048 is simply a fraction of 1 over 16. So 1 over 16 is equal to a sub 1. Now we have this piece of information, 1 over 16. What's the last step? Let's write the explicit formula. A sub n equals 1 over 16 multiplied by the ratio 2 raised to the n minus 1 power, and that is our final answer. Now, just to quickly wrap up, as I always like to in my videos, explicit and recursive formula, definitely have those memorized, right? Simple formulas. Explicit comes in one neat package. Recursive has 2 parts. You need a base case. You always need a starting point, and you need the formula for it. And also remember the summation formula. That's probably going to come up a lot less when you're dealing with geometrics in an algebra class. It comes up a lot in other classes. However, it's still important to memorize for the rare instance that it is used. The general idea for a lot of these questions, know how to get the explicit formula, right? Know how to get a sub 1 and know how to get r, because then you're able to write the explicit formula, which allows you to pretty much go anywhere. You can go from the explicit to the recursive. You can use the explicit to find a sum. You can use the explicit to find a specific term, like the 8th term, 10th term, 52nd term. You could use the explicit to do that last question we did that involved, hey, here are 2 specific terms, write the explicit, right? It's all about having these 2 pieces of information, the first term and the common ratio. All right, so that's pretty much it. Thanks for watching. If this helped you, hit a like button, hit the like button. Definitely helps me. But other than that, good luck.